All right, what's up, physics students? I'm going to go over number 4 from the scenarios that we looked at today dealing with the conservation of energy. This was probably the most complicated scenario that was on there. So when we're dealing with problems with conservation of energy, what we need to look at is that the total energy before an event is equal to the total energy after an event. And when I'm talking about total energy, I'm talking about total mechanical energy. And we have those 3 types that we all know and love. Okay, so this small equation here can get broken down into a bigger one, and we can just throw in all of our known types of mechanical energy. So we have elastic potential energy is equal to gravitational or plus gravitational potential energy plus kinetic energy before. Okay, so all of these before an event are equal to all of them after an event. So we just write all our types of mechanical energy out like this. Okay, so now this equation looks big, long, and scary, but when we actually look at a problem, we can isolate what types of energy are actually there before and after some event. All right, so in this problem, we know that the jack-in-the-box guy is being compressed down, so that is elastic potential energy. So we look at him, we look at this guy right here. Now what about gravitational and kinetic? Well, there is none there. So we get rid of these guys. We say scram, sayonara, get out of here. So all we have on our left side in this problem is elastic potential energy. Now on the right side, or after the event, the jack-in-the-box guy is released. So that stored energy we have in the spring, well, that's gone now. But that energy has been converted into kinetic energy, which we automatically know because I'm asking you to find velocity. But then there's also some gravitational potential there. So our right side, or our energies after the event, are gravitational potential and kinetic. So we can rewrite this big, long equation here, and we can just say that elastic potential before is equal to gravitational potential plus kinetic energy after. So big, long, scary equation, shorter, less scary equation. I'm going to erase some of this stuff, and we're just going to focus on this equation to solve this problem now. So what do we have? We had elastic potential is equal to gravitational potential plus kinetic. And now we extend these out and just plug in our known equations for all these types of energies. So our elastic potential, what do we have? We have 1/2 k change in x squared. And that equals our gravitational potential equation plus our kinetic energy equation. Now I have our known information up here, so we can just plug that into this extended equation here, and we can say that 1/2 times our spring constant, 80 newtons per meter, times our change in x, which is our 0.08 meters, and that's squared, is equal to, well, we know the mass, we know gravity, but what about this h? What is this h value? Well, that jack-in-the-box guy was compressed down some distance, right, 0.08 meters, but then he was released, and he actually gained that change back. So we actually consider this 0.08 meters, our change in x, but also our height. Okay, so in reference to his compressed position, he gains this height back. So he has that gravitational potential from that height. So we'll throw our numbers, our known information in here. And we're running out of room. Okay, and then we know that we have our kinetic energy tacked onto that as well. So we can simplify these numbers down. I have the calculations here. So this side is going to equal 0.256 joules, and that is going to equal 0.039 joules plus are 1/2 mv squared. So now I'm gonna erase this stuff up here, and we're actually gonna solve for our velocity now. Alright, so we have our 0.256 joules is equal to 0.039 joules plus 1/2 mv squared. So now we just subtract this from this. Okay, so we subtract our gravitational potential from our elastic potential. So that gives us 0.217 joules is equal to 1/2 mv squared. Now to simplify this down, we just multiply both sides by 2. And then we also divide by our mass. Okay, so what is this going to look like? It's going to be 2 times 0.217 joules divided by 0.05 kilograms is equal to velocity squared. Take the square root of both of those, and we end up getting for a final answer that the jack in the box was going 2.94 meters per second. So 2.94 meters per second is our correct answer for this problem. So just to reiterate, we want to use that big long equation where we have all of our types of mechanical energy listed, but the really important thing is to figure out what the event is in this problem, where we can figure out what types of energies were used before that event and what types of energies are after that event. And that'll make our lives a lot simpler. So I hope this helped. Take care, physics students. Have a good weekend.